Right, so the question that my slides would like to answer is whether we can fit Linux on a floppy disk. So I didn't have this introductory slide before, but I decided to make it anyway. And if you know me, then there's very little I could tell you that would make this slide worthwhile for you. If you don't know me, then I don't think I can introduce myself in just a single slide. But I am a computer science student in my final year of bachelor's from Germany. I'm looking to start a PhD next year, actually. I'm mainly interested in data compression, compiler construction, AA or ML, reverse engineering, theoretical computer science, code golf, and numerical algorithms. I also like cryptography, not necessarily crypto, but cryptography is okay. Retrocomputing and operating systems. So as a fun fact to those of you who know me, who want a unique fact, I really want to be a comedian one day, and I think that it goes in line with my interest in machine learning. So I'm just like looking at the people here. Many of you have probably interacted with one of those fascinating devices before in your life. So the capacities of those pretty popular storage media are quite large. For instance, my first thumb drive was, I think, about 4 gigabytes large. And all of them are pretty common boot and installation media. I'm pretty sure they have a Debian install USB stick on myself right now. But the question is, do we really need 4 gigabytes to fit in an operating system? Especially a modern one. So here's some prior art. As you can see, we have damn small Linux, which is actually not that small. It's actually the biggest one on the list. It's about 50 megabytes, and it's a live C distribution. It's then succeeded by TinyCore Linux, which is 17 megabytes. Still quite large, but much smaller. It's perhaps the most popular minimalist distro. If you ask a question on Reddit or something, like, what's the smallest Linux distro, out of curiosity, this is probably what they're going to link you to. And the smallest one I could personally find that's still kind of usable is Nano Linux, but unfortunately that was discontinued. And what I really wanted to say is that all of those are quite large, even despite the fact that they seem to be pretty small. They provide a lot of really nice features like web browsers, text editors, and games, and even a GUI, perhaps. And another big problem is that they also lag behind kernel versions. So they use kernel 4, kernel 5. Right, so what if we didn't want any of those nice features? What if we wanted just some nice features, but perhaps not that many of them? And as a goalpost of this experiment, we'll use this device. I'm not sure how many of you are familiar with this thing. So this thing is capable of storing about 1.44 megabytes of data, which is 0.2% of a standard 70 megabyte CD-ROM. And the best widespread contender, TinyCore Linux, needs about 10 of those to boot, which would be pretty impractical to switch 10 floppy disks if you want to boot Linux. So if we want to fit Linux on a floppy, we are going to need a toolchain. It's pretty clear that we're going to have to compile the kernel ourselves, or we have to compile everything ourselves, in fact. And for that, we'll need a specific toolchain. So we're going to use, we're going to build 32-bit x86 code for the very particular reason that 32-bit code tends to be smaller. It's also easy to model. And 32-bit x86 code doesn't natively support that many ISA extensions. So the kernel would probably not be tempted to include, RDRAND, RDSeed, and AES extensions, which are probably going to cost us a lot of space. So we just don't want any toolchain, because that's obviously not going to work. We are going to settle for the non-GNU option, which is Muscle. And it's a pretty lightweight C library, which is much smaller and mostly compatible with glibc. And the much smaller aspect, to be honest, speaks to me much more than the compatible with glibc aspect. I think I would make it work nonetheless. But here we have the final triplet, i46 Linux Muzzle GCC, which I'm going to use for my Linux kernel. And in case you want to follow along, you can get this toolchain over there. So just as an experiment, here we have a very simple program in C, which notably doesn't pull vprintf, printf, etc., which means that it's much smaller than a regular program that. Where are the braces? Than a regular program that would actually use printf. So we compile it with the static libc, obviously, because we are probably not going to have a dynamic linker on our floppy Linux. And we also optimize for size, and we end up with a 4.9 kilobyte binary, which is pretty good, but we'll get back to that later. So let's try to get something booting. And by something, I mean just like, anything. So the specific kernel version I would choose is the newest one, because there are already many distros that use ancient kernels. I think that this makes the process of fitting Linux in a floppy disk much easier. But we want a little challenge, because why not? So how many of you have compiled the Linux kernel in any situation? There we go. Excellent. So you probably know how it works. It's pretty basic nitty-gritty, so you have to take a config. For most distros, the default config actually doesn't work, but because we're making our own distro, it doesn't really matter. So we copy over the default i386 config, we enable TTY and printk, just to see if something fails. We'll have a way to see what exactly failed, because this will be a recurring issue, things failing. So before we boot the kernel that we prepare using this command, we need an initial RAM disk. And this is where things like the shell or like the demo programs are going to go. But we still have to prepare it. And just to get something running, we're going to put our hello world on this init.rd. And we CPIO it up into an archive, because that's the standard format for init.rd images. And it boots. So we can boot it with QEMU, we can set the kernel, we can specify the init.rd, and it works kind of nicely. So the caveat is that it's at 10.8 megabytes, which is more than a floppy disk. And in fact, it's much larger than the default Rust and Go hello world binaries compiled. So it's not a very good outlook for us right now. So before we start removing crap from the kernel, which is the most logical step from here, we want to make sure that we don't actually break anything useful while doing so. And to do that, we're going to build a proper initial RAM disk using BusyBox. And then if we remove something, it's easier to tell if something breaks, because then it won't boot anymore. So we're going to use BusyBox 1.35. It's quite large, about 1 megabyte. But it contains a lot of useful tools, and we'll kind of get back to that in a second. So this is the init program. This time the braces are not missing. I don't know what happened in the previous slide, but this is our init program. So the idea is that we mount some important file systems using mount. We install BusyBox. So BusyBox install basically puts you a bunch of symlinks to things, symlinks specifically to shell in the standard Unix directories. And then we just launch the shell. We launch the shell with the init script, and the init script is like nothing fancy. It just disables the annoying printk and funnels into the message. And also it's going to enable OpenVT, but more about it later. So this is where we are right now. We have printk, we have a BusyBox. We have a Linux kernel booting, and it's very nice. So we have a Linux system that fits about 11 megabytes, which is smaller than Nano Linux, but unfortunately there is nothing here. So what do you want to do about this? Well, the next two logical steps is removing the size of the biggest offender when it comes to the code size, which really turns out to be the kernel. So we'll start by using XZ for compression instead of the, I guess, pretty default gzip compression. And we're going to disable the support for all the codecs except gzip for init.rd. And we change the compile flags to size optimizations. And these changes alone actually bring us down to 6.7 megabytes. It's still not quite the Rust hello world. So we are pretty far away. So let's see what goes next. So this step is also pretty logical, just like remove everything that we don't need. And that alone actually lets us fit on the floppy disk, which is quite amazing. We don't actually need to do anything. If we use XZ for compression and we specify the frame format that the Linux kernel specifically uses, then we end up with a kernel plus initrd being about 1.28 megabytes. So it fits. So nominally, the presentation could end here, but that's pretty boring, and I'm pretty sure most of you could also do it. So let's continue. That's very nice, but we can't do anything with our kernel other than idling in the shell. So I personally don't like V. I prefer Vim maybe, and I would like to have cool things in my init.ramfs to play with. And we actually haven't figured out how to make it boot off a real floppy, right? Like we still pass those 2 arguments to QEMU, and it's not booting yet. So now that we have the MVP, this is our goalpost. We want to have a bootable system, bootable floppy disk. We want more stuff in the intramfs and want more features in the kernel. So eventually we're going to run out of space. There's not much left. And then we'll move on to the magic of making our own kernel compression algorithm. So the floppy Linux is actually going to support networking. We'll specifically support the Intel E1000 network card and compatible. We have the TCP IP stack, basic security features, DNS resolvers, etc. So who could have expected that the kernel grows in size? Unfortunately, it does. And also configuring networking with BCBox is tricky. I mean, at least to me. I haven't built my own Linux distro before. So this is a script I use to connect to the internet. And would you look at that? We can ping the Cloudtrail DNS resolver. We don't have DNS yet, but this will change. So as a checkpoint, this is what we have right now. We have print-k, ISA support, read-write block layer, compacted memory manager, and PCI bus support. We have SATA, ATA, SCSI, E1000. We have IPv4 networking, DNS resolution, FAT32 file systems. So you can kind of mount like your favorite Windows 98 hard drive and mess with it in Linux. So we have a BusyBox and everything that BusyBox comes with. So, you know, a HTTP server, DC, BCA, WK, a shell, wget, vi, sed, etc. So the basic idea for how we want to overcome this issue of the kernel being too large is, well, first we're going to put it in the same logical container. So in Linux, you can, in menu config, you can actually specify the location of the initrd file, which is very convenient. And nominally, adding our own compression feature to Linux is not that difficult. However, I'm not as familiar with Linux kernel as a code base, so that will become interesting soon. So what we're currently looking at is like a somewhat fast compression algorithm that can beat XZ quite significantly, which is a pretty big requirement just from the start. And we want it to not use a lot of memory and actually run on 486. So that makes it even more difficult. And on top of all that, the compressor itself must be pretty small, because otherwise it cannot be compressed, right? The compressor cannot be compressed. So the problem is that if the compressor is too large, then it kind of negates the compression ratio gains that you would otherwise get. So for how it works, well, a bunch of nerd stuff, I guess. I don't want to really bore you with the details of how compression algorithms work. I'm pretty sure that if you wanted to, you could like kind of figure it out yourself. But here are some common ideas. If you understand any of those words, please approach me after the presentation. So we have a binary arithmetic covering-based statistical compressor. It's a mixture of final-order Markov models, and we have a match model for machine code that seldom disables the mixer. The mixer uses gradient descent in the logistic domain. Then we have a bunch of secondary symbol estimation passes filtered by the A89 transform, which I actually talked about last year, if you remember. So the biggest issue with this code base that I wrote is actually integrating into the Linux kernel, because remember that we don't have anything. Like, we don't have a memory manager when the system is booting. That's the point, right? So we really want to make this as simple as possible, because otherwise it either won't fit or won't boot because of how restricted the environment is. So I don't want to go into too much detail. I told you this already. But the decompression step was quite easily produced in a few hours. It's somewhat fast, 20 seconds to code the kernel. It's worse on actual i486 machines, but we'll get to that later. But most importantly, our amazing Linux distro with networking currently fits into a floppy disk, and we have a lot of spare space. So here we have 2 more goalposts to score. We need a more standalone bootloader, so we need perhaps a boot sector, because grab is quite big. It supports a lot of modules, but the best I can do is like 500 bytes. So grab is kind of out of question. So the bootloader was actually written from scratch in real mode x86 assembly. It's only above 300 lines of code. So there are a few difficulties. For instance, the A20 gate, which is something that grab handles by itself. So some of you might be old enough to remember MS-DOS, right? Maybe, maybe not. So the issue is that back in the IBM PC era, a lot of software abused the fact that the memory wraps around, right? So if you go past the first megabyte and then go one step more, then you go back to 0, right? But if you have more memory than 1 megabyte, then it's not, technically speaking, not 0, right? So there's this gate on the 20th pin of the CPU, which enables or disables the megabyte addressing mode. And because we want to have memory, we have to enable this, and the kernel also expects this. So we'll be operating in Unreal mode. So we load the GGT, but turn off the protected mode bit in the CR0 register, and we read the floppy disk sector by sector and relocate the kernel to where it expects to be loaded. So with my sloppy and rush programming, that took 2 sectors, and that's an acceptable size for a bootloader. So let's continue. Excellent. So this is the direct download. Some of you have laptops, maybe. It's a Linux conference after all, so you can download this and play with it together. So this feature has a flat assembler by Tom McGrister, which is actually my favorite assembler. And as an alternative, you could add some other large program to the initrd, but I just didn't see the reason. And having some sort of a development tool helps us bootstrap, perhaps in the future. So this is what you have in the image. I'm not going to read that out, absolutely not. You can maybe look if something catches your eye, like perhaps the networking stuff, diff, patch, find, grep, decompressors. You have RPM if you wanted to install Fedora packages on your floppy Linux for whatever reason. And the kernel. Yeah, we have quite a bit of stuff as well. We have a 2048 game, we have chess, we have a demo. And of course, what would it be if we didn't test on real hardware, right? I didn't bring any interesting retro tool today because unfortunately, hard disk drives are very fragile, and I don't trust the Frankfurt airport to keep the hard disk platters in a single chunk after I get my kernel luggage back. So this is the machine we're testing it on. The decompressing takes about 6 minutes on that ancient machine. That's almost as much as it takes to compile a Linux kernel on my machine, by the way. So here you have the 2048. Here you have the directory listing. Here you have the donut. And I'm going to regret this, but let's do a live demo. So I just need to move my terminal right here. I don't actually see what I have here on my screen because there you go. Right, so it takes a while to decompress, but thankfully my laptop is quite fast. This needs 70 megabytes of RAM, which sounds kind of unreasonable if you're not super familiar with how retro computing generally is. But that's not an unreasonable amount of RAM for a 586 PC to have. So we're just going to roll with it. This is probably the boring part, right? It's like, you know, you're using a mainframe, right? And you're typing characters one by one and you're waiting it for load. I actually knew someone who used the TTY that was routed overseas through a deep sea cable, and they had to wait 15 minutes for their things to return syntax error, right? So this is what we have. It's not that much. So MISCbox is the C program with all the weird stuff inside. So we have the donut, of course. It's a pretty standard C demo of 3D graphics. If we go back, you'll see that. Damn it! You will see that we have much more here. We have actually a HTTP server. We have some system management utilities. Just to give an example of cron, in case you wanted to, schedule things in floppy Linux for any reason, really. So to demonstrate to you that this is like an actual Linux computer, right? I'm just going to. Compile a very simple program. So this actually uses the Linux kernel interrupt to print something in the screen, right? And the best part of this presentation, I think, or perhaps this floppy Linux, is that we can do this. So the question is whether networking is going to work here. This is the curse of like live demos. Like, what if something breaks? But it didn't seem like it broke, so we can actually try it. We can ping the DNS. Something is wrong with BusyBox and it pings only once. If you know what this is caused by, then I'm really going to appreciate you telling me. We also can duplicate things, like this is an example of a domain resolution, perhaps. So we're going to download the front page of Google, and we can open it in VI. That looks like Google, but I don't think that you're supposed to be able to render this in your head. I don't think that anyone is capable of doing that. So just to show you, we have like sed, awk, we have grep, we have find. We don't have fun. We have find. Yeah. So you're welcome to download this and try booting it. I'm going to release my grab and kill the VM, if that's even possible. Right, there we go. Okay. So where do we go from here, right? That's an excellent question to ask. Where do we go from here? Well, you can remove some stuff from BusyBox that you don't like, I guess. As a next step, you can try to make it more streamlined. You can add a rise to it. You could add your own dot profile. You could make it funny. You could bundle more stuff like terminal games. You could have some interpreters and compilers. You could have system rescue tools. Or you could perhaps write a package manager for the floppy Linux, right? So the way this would work, in my mind, is you have this tool chain, right, that can compile source packages. And you could fetch the source code, because the source code is actually probably small enough to be stored on there, and compile it from scratch. This is actually how TCC boot works, if you're familiar. It's a bootloader for Linux that actually compiles the kernel from source code in order to boot it. It's a very interesting tool. I actually tried to feed TCC on this floppy, but I kind of failed. Let's continue. So this was a really short talk. I don't want to bore you with compression. I don't want to bore you with academics, because I'm pretty sure that this is not why you came here. So those are my contacts if you want to reach out to me. And I hope that you like this talk. Unfortunately, due to the fact that I'm working on my thesis and I kind of have to move out soon, I couldn't spend that much time on the slides and on the code. I started working on the source code decompression algorithm on Monday, a few weeks ago, and I was finished by Wednesday the same week. That kind of explains why the performance is not top-notch, but I tried. Anyway, thank you for attending.
We have a few questions for you. The first one is dev/shm and run it?
That's a very good question. I mean, okay. So I tried to enable frame buffer support because I wanted to show like a really nice demo scene kind of thing. I'm actually going to revision next year if you want to meet me there. I wanted to show you a demo, but the reason why I didn't show a graphical demo is because I couldn't enable the frame buffer from the kernel. I tried everything, and it just wouldn't spawn the frame buffer device. I even tried to create myself, and it wouldn't appear. It wouldn't work. They said that there's no such device. So you would have to mess with it a little bit to make Doom run on it, or you could perhaps ASCII modify Doom to have those silly terminal graphics. But not really as it is, but it should probably be easy to do if you're better with Linux than me.
Okay, the next question is there enough space for Lynx browser?
Excellent question. Yes. So if you chose to remove some of the funny stuff, like the goddamn donut and the 2048, which I actually forgot to show you, then you would have, I think, about 80 kilobytes of compressed space. So that kind of translates to like maybe 160 kilobytes. If you can fit links in 160 kilobytes compressed, then yes. If you can't, then no.
The next question is fitting on a 5.25-inch floppy next?
Nice. I like some challenge, and I would really love to do that, but I don't really own a working 5-inch floppy. So if any of you wants to donate an old floppy drive for science, I'm I'm up. I'm here. So probably.
And the last one, more of a suggestion. Put Malbolge Lisp there and it will be complete, right?
I wish. If only we could compress it down to such a small size. But yes, it will be complete. You'd have the real mainframe kind of vibes from it, right? Like it takes 6 minutes to boot, and then it takes 2 minutes to evaluate 2+2. So you could say that it's pretty authentic, pretty good for retro computing enthusiasts. Thank you for the questions, and thank you for attending.
We got another question just right now. Next, we need to boot from analog media like vinyl.
Okay. All right. So I think that this could be doable. I mean, you know those cassette tapes, right? That you could buy music on, right? In places. That's actually an element of my childhood. Yes, I'm actually that old. But you could probably fit it on there, and it sounds like a joke, but it really isn't. But a lot of people use magnetic tapes for backups because they are very cheap and they're very efficient when it comes to storage capacity. So that could not be as much of a challenge as you're imagining it, but a real vinyl, probably yes.
Okay, thank you for the answers and for the talk. Those were all the questions.
Thanks for attending.
Thank you.